Good morning. I would like to welcome everybody back to the 2017 Cuba Infrastructure Scholarship Competition. I would like to remind everyone again that this is being broadcasted live at El Diario de Cuba, and we very much welcome every commentary or questions to the teams and or to the association. We're more than happy to comment on those here in between the groups. And but at this time, we will proceed with the fourth team, and this team is coming from Florida Institute of Technology, M-Wed, Magnetic Wave Energy System Device. They will be presenting on the self-sustainable magnetic wave energy device. The teams are composed of Mr. Erwin Horvath, Abraham Butla, Julie McCarthy, and Alex Ortiz. Their industry and faculty member is Dr. Elena Solo Gabriel, and at this time they will start on their presentations. Thank you.
Good morning. In 1492, Cristobal Colon sailed the ocean blue. Now, we all know how that story goes, especially if we're from this side of the world. However, not many of you know what happened 5 months prior to that. Spain had just gotten out of several hundred-year war, and the infrastructure was not up to par with some of the European neighbors at the time. And they still took the liberty of investing in 3 ships across to the unknown. Now, I compare this to Cuba's situation in the sense that the nation is coming out of a very complex history. Their infrastructure is not up to par to where they desire to be. And based on where we are here today, I take pride in saying that the initial steps have been being made to make Cuba a much brighter future. Now, for those of you that I haven't had the pleasure of meeting today, my name is Alexander Ortiz.
My name is Erwin Horvath.
And my name is Ibrahim Bootwala. We are 4 undergraduate ocean engineering students from Florida Institute of Technology. Unfortunately, we're missing one of our team members today, Julie McCarthy, who made tremendous contribution towards this project. We would also like to thank Dr. Stephen Wood, our department head of ocean engineering, for his determined support, and Dr. Solo Gabriela for her continuous guidance throughout this competition.
Okay, to start with a brief mission statement. Our goal is to help make our species independent from the reliance of fossil fuels. We plan to do this by implementing the reliable, clean source of energy for not only the government agencies, but for the consumer market as well. So now, before we can incorporate our strategies to Cuba's energy infrastructure, we had to do a little research on the country. So the island nation of Cuba has roughly 11 million people, and for the growth of the population, we can expect the energy demand to increase along with it. Now, Cuba is heavily reliant on foreign oil, as with many countries nowadays. And in 2015, Raul Garcia Barrero, a senior official from Cuba's energy ministry, made it clear that it's getting off foreign oil a high priority to the nation. The Cuban government also plans that by 2030, sustaining 24% of the country's energy needs solely on renewable resources. Now, this sum is pretty large, and the M-Wed team would like to contribute to the Cuba's goal by implementing the feasibility and simplicity of our senior design device to offset the cost of dependence on oil.
So, what is M-Wed? M-Wed stands for Magnetic Wave Energy Device. It utilizes the concept of Faraday's induction, and basically Faraday's induction is when a magnet oscillates through a coil producing EMF. EMF stands for electromagnetic force. So as you can see in the image here, we have 3 magnets. We also have a small scale model on the judge's table. We have 3 magnets. The first one is fixed, the second one is moving, and the third one is fixed as well. The middle one is connected to this shaft. So as it oscillates through this magnet, it produces some EMF, and due to the repulsion forces, because it's in an antipolar formation, it goes in the other direction and it constantly oscillates back and forth. So the kinetic energy from the wave exerts a force upon the plate and causes this device to oscillate. We can do the same thing in a vertical orientation. So analysis, here are some examples of what we decided to do with our device. Initially, we decided to 3D model to make sure that it is in fact buildable. We also ran CFD, which stands for computational fluid dynamics, in order to determine the drag coefficients on the plate. And finally, we ran structural analysis to determine any stress points and strains on our device. The most significant analysis that we've done is magnetic analysis. So in the image here, the blue area represents as the magnet surpasses the coil and it produces some voltage. That voltage, according to a software that we use, which is called FEMM, it stands for Finite Element Method Magnetics, showed that in one oscillation we can produce 110 millivolts. If we assume that this device can oscillate 1,000 times per day, it would generate about 110,000 millivolts. If you convert that, it is 110 volts. Utilizing Kirchhoff's power law, we take the 110 volts, we receive 3 amps from the software, and we get 330 watts per device, which is approximately 0.33 kilowatts, or in other words, 7.92 kilowatt hours per day. In 1 month, its efficiency is 237 kilowatt hours per month. To put things into perspective, the average household in the US utilizes approximately 908 kilowatt hours. We can achieve this value with 4 devices. Due to the harsh environments of the ocean, we chose aluminum 5083, which is a marine grade series alloy with high strength. The table shows the percent compositions of different elements in the aluminum alloy. Corrosion is a problematic factor when building ocean-based devices. To counteract bimetallic corrosion, we will sleeve our copper coil. We will also sleeve any screws that will mount the device to any surface. And in order to ensure longevity of our device, we'll be applying something called an anti-fouling paint to prevent biofouling. Biofouling is the growth of microorganisms such as tube worms and barnacles, anything that's placed in the water, so on hulls of ships and such. So welding itself introduces a lot of stress points in our device. We decided to pressure cast. On the image on your left, you see something called crack propagation, and due to the ocean, waves exert forces in the X, Y, and Z direction. So to be on the safe side, we decided to pressure cast. On the image on your right, you can see how pressure casting is done. Basically, you make a mold of your device, you place your molten metal into the container, it goes through the refractory tubes, and your device is created, and then cooled. Simplicity was also a very important factor of our device. You can see that we have a 6-piece assembly. The initial piece is the shaft shell, where the top magnet goes into it and it's fixed at the top. The bottom seal goes onto the threaded shaft here. Then the bottom magnet gets placed on top of the bottom seal, which goes onto the threaded shaft. The middle magnet is then threaded to the shaft, and all of this is put together to give you the device that you saw earlier and the device that is on the judge's table. So this is our bill of materials. This takes into consideration current market prices of aluminum 5083, copper, as well as casting services. The casting services were determined from various companies throughout the state of Florida, and one device costs about $3,500 to produce. So earlier in the magnetic analysis, we said that we need 4 devices in order to produce the same as a US average household. So it would cost approximately $14,000. According to FP&L, in the US, we paid 12 cents per kilowatt hour. So in about 10 years, that costs about $13,000 to $14,000. So your return on investment for 4 devices would be about 10 years. And this is our Gantt chart. This just shows the progress that we've made in our research. Currently, we're at week 31, 32. So you can see that we've gone through all of these sections, including our abstract, 3D modeling. We will always continuously run analysis to make sure that we achieve the best efficiency. And we will soon be entering phase 3, which includes construction and assembly.
The 2 pictures, as you can see, the 2 pictures, they represent the wave characteristics of the Caribbean region. The first picture represents the currents that flow through this region, that are the Gulf Stream, the Mexican current, and the Louisiana current. These currents, they help to establish the wave direction. So the picture 2 represents the wave direction, and the arrow represents the wave direction. So the wave flows from the northeast direction with an average height of 5 feet, and it goes towards the southwest and the northwest regions. But the northwest region has this swell, which is caused generally due to the storm and the hurricanes, which increases the wave height of approximately 9 feet. These waves, particularly, they generate big waves, and these big waves are not necessary for our device, as our device requires small waves and oscillations which moves the shaft easily due to the force caused by the magnetic field. The northeast region also has the swell, but the swells are reduced due to the Bahamian islands, which reduces the wave height to approximately 5 feet, which is suitable for our device. In the northeast region, our device can be installed at Varadero, Puerto Padre, and Baracoa regions. This is a seawall where our device will be mounted horizontally. As the wave hits the plate, the magnet attached to the shaft will oscillate between the two antipolar magnets and will generate some energy. This is a seawall in the Puerto Padre region where a device will be mounted in a horizontal direction. Our device can also be mounted just below the dock in a vertical direction where the waves would hit the plate and the plate will go down and the magnet would oscillate between the two antipolar magnets. This is a dock, sea dock in the Hotel Brises, where a device will be mounted just vertically below this walking dock, and the hotel. Just below that, we can also attach a device. And
so some of our other accomplishments that we've done is we worked with the NASA JPL sustainably and environmentally friendly conference at Pasadena this last year. And some future outlooks is that we also plan to attend the conference in the Netherlands coming up. These are our references, and thank you. Can I ask any questions?